In this tutorial, we will explore the differences between two fundamental ways to control a robot's movement: joint mode and Cartesian mode. For joint movements, you specify the desired joint positions directly. You control the robot in joint mode or, as we often say, in joint space, when you don't care about the precise path of the robot end effector. For example, you move the robot in joint mode when you want to move from a retreat position to an approach position, far from obstacles. You also move the robot in joint mode to a given set of joint positions, which may correspond to a singularity. However, you often need to specify the position and orientation of your robot's end effector directly. We say that you control the robot in Cartesian space. Defining position in space is straightforward, and we won't discuss this. Defining orientation in space is much more complicated. That's when the Euler angles come into play. Beware that there are multiple Euler angle conventions with various definitions. We use the XYZ intrinsic, also called body-fixed, convention. In that convention, Euler angles alpha, beta, and gamma are defined as follows. We first rotate at alpha around the body x-axis, then at beta around the body y-axis, and finally at gamma around the body z-axis. Euler angles have many peculiarities and are very different from position coordinates. For example, there are two or even infinitely many Euler angles representing a given orientation. We invite you to read our tutorial on Euler angles for more details. The x, y, and z position coordinates in the three Euler angles define the pose of one reference frame with respect to another in space. We will discuss reference frames in a separate video. When you specify a target pose for the robot end effector, the robot controller automatically calculates the required joint positions based on configuration parameters that we will cover in a separate video. You're now ready to learn about the movement commands allowing you to move your robots. There are a few different types of movements that are supported by Mecademic robots. Movements where the robot joints move linearly in joint space are also called point-to-point moves. They will allow the robot to reach a specific position in joint space as fast as possible. All the joints move to reach the final position simultaneously, and the velocity is only limited by the slowest joint. Therefore, it's the fastest type of movement a robot can do. The drawback of this type of movement is that the user doesn't have control over the end effector path. It completely depends on the starting and finishing pose, and will usually move unpredictably since it takes the path of least resistance for the joints. With move joints, you specify the target joint positions directly. With move joints rel, you specify a relative or incremental move. With move pose, you specify the target pose of the end effector, or more precisely, the pose of the tool reference frame with respect to the world reference frame. The move pose command, however, is still a joint space command. Before starting the command, the robot converts the target pose to a set of joint positions and then executes internally a move joints command. Because there are several possible sets of joint positions, you need to specify the so-called posture and turn configuration parameters. Alternatively, you can leave the robot to find the set of joint positions that is fastest to reach. These three joint space commands can be affected by changing the joint velocities and accelerations. The following commands can be used. As mentioned, the move pose has some settings that affect its movement, such as the frame of references set TRF and set WRF. The other settings specific to move pose are the configuration settings, set autoconf, setconf, setconf turn, set autoconf turn. These settings will be explained in detail in another video. Other than joint space moves, there are Cartesian space moves, such as move lin. This movement is expressed in Cartesian space and forces a specific Cartesian path to the end effector. For the same starting and ending robot positions, a linear movement will generally be slower than a joint space movement. The drawback of move lin is that it's sensitive to singularities, but this move is still required for some applications. All in all, Cartesian moves can be thought of as a series of very small joint movements that cause the end effector to move in a specific path. The following commands can be used. The arguments of movelin are the target pose of the TRF with respect to the WRF. With movelin, the origin of the tool reference frame, i.e., the TCP, tool center point, moves along a straight line. If the target orientation is different from the initial orientation, the orientation will be modified along the path using a minimum torque path. Move-lin-rel WRF is a relative linear move very similar to move-lin, but the arguments are relative poses with respect to the current pose of the TRF, but relative to the WRF. For example, if you execute move-lin-rel WRF 10, 0, 0, 90, 0, 0, the robot will translate its TRF 10 millimeters along the x-axis of the WRF while rotating a total of 90 degrees about the y-axis of the WRF. Move-lin-rel TRF is like move-lin-rel WRF, but the relative pose is expressed with respect to the TRF. Linear moves can be affected by changing their velocity and acceleration. These following commands can be used. There are some things to note about linear movement velocity. While it's possible to specify velocity values for linear moves, there is no guarantee that the robot will reach them since it does not pre-compile the program to check if all the moves are possible. It's all done online. If the robot cannot reach the velocity target, it will go as fast as possible. This happens more often in higher velocities because of the robot's size, so we recommend always testing your application at full speed when validating. So far, we only discussed what we call the position mode motion commands. We also offer another set of movement commands, where instead of joint positions or end-effector poses, the user specifies joint velocities or end-effector Cartesian velocities. Unlike the position mode commands, the velocity mode commands do not wait for the previous one to be completed before executing the new one. If a new move in the same space is sent before the robot stops, the previous function will be overwritten, and the new velocity will be blended. If the new move is in a different space, the robot will fully stop before moving again. The velocity control settings are as follows. The acceleration is set by using the same functions as the position control. Because the movement is specified as a velocity movement, a movement time has to be specified. A timeout command is used to specify how long the movement should continue before stopping. This mode is ideal for things like jogging panels. As long as the user presses the button, the program can keep sending the velocity command and stop when the button is released. The robot will then stop after the timeout is over. It can also be used with external sensors such as a force sensor. The robot keeps moving constantly until the sensor is triggered and the program stops sending the commands. The robot will then stop after the timeout.